Good morning. Welcome to our 9 a.m. press conference, our first of the day. This one we've entitled NASA's Lunar Twins, GRAIL's First Science Results. And that's because there are the first science results from GRAIL. Our speakers in the order in which they will be speaking are Maria Zuber, GRAIL Principal Investigator from the Massachusetts Institute of Technology in Cambridge, Mark Wieczorek, GRAIL Co-Investigator, University of Paris, France, Jeff Andrews-Hanna. He is a guest scientist at the Colorado School of Mines in Golden, Colorado. And Sami Asmar is GRAIL project scientist and co-investigator with the NASA Jet Propulsion Laboratory in Pasadena, California. Dr. Zuber will lead off.
Okay, thank you very much. If I could have the first graphic here. So on behalf of the GRAIL science and mission team, it is really my pleasure to present to you the first scientific results of the GRAIL mission. So GRAIL is a dual spacecraft mission. It's a satellite-to-satellite ranging mission. The reports that I'll be presenting today, which reflect 3 papers that are coming out in Science, deal with data that was collected during GRAIL's primary mapping mission between March through the end of May of 2012. So the 2 spacecraft send radio signals towards each other, and they are detected, and we measure the distance change between the 2 spacecraft, and we've actually measured those distance changes to 50 nanometers per second over the course of the mission. So that is 1/20,000th the velocity that a snail moves. Okay, so we are able to measure extremely fine changes in the distance between the 2 spacecraft, and because of that, we have a sensitivity in our measurements that is 3 to 5 orders of magnitude over any previous gravity study of the moon. So that's not 3 to 5 orders of magnitude improvement. So the next chart, so because of that, we were able to make significant improvements in lunar gravity. The 2 previous studies that have measured lunar gravity that have been used for scientific purposes are the Kaguya mission, which used a relay tracking satellite to get far-side gravity, and the Lunar Prospector mission. This is a map of Lunar Prospector gravity shown up here. The units are milligalileos, where a Galileo is a centimeter per second squared. Red corresponds to mass concentrations, blue corresponds to mass deficits. And if you can see the red bullseye structures there correspond to the mascons, which we've known about since the 1960s, that tugged satellites out of their orbit as they were doing reconnaissance to find landing sites that the Apollo astronauts could go to. And if we go to the next chart here, you can see the improvement that we get from the GRAIL mission. So, so this particular gravity field has a spatial resolution on the lunar surface which is as good as 13-kilometer block size. So we, in this particular model, we resolve all craters on the moon greater than 30 kilometers, many craters on the moon less than 20 kilometers in size, and this actually means that we're in the realm of detecting simple craters, which are the most abundant landform on ancient planetary surfaces. We resolve not only craters, but structures of craters and basins on the lunar surface. So we resolve basin rings, ejecta blankets, central peaks, as well as individual tectonic structures. So, so we have essentially taken geophysics, and we are bringing it into the realm of surface geology, because we can actually do quantitative geophysical analyses of individual structures. So the next chart here is a video which shows the gravity field of the moon. So you can see the large mascons there, but as we come to the moon's far side here that we don't see from Earth, you can really see the abundance of short wavelength detail here, which, quite frankly, the team is only now beginning to study. Now, one of the things that we want to do with gravity is probe to within the inside of the planet. And so what we want to do is subtract away the gravitational attraction of the surface topography on the moon, and then whatever's left tells us what's inside. And that's shown in the next video. This is something that we call Bouguer gravity. And immediately you notice, you see the bullseyes that are associated with the lunar mass cons, but look at how smooth the moon is gravitationally. And the reason that that is the case is because we have all known that the moon and other terrestrial planets have been bombarded significantly during their history. And the only way that you can get the inside of the moon being that smooth is if these impacts have pummeled and shattered the upper crust of the moon. So here we see now a picture of the moon being far more broken up and shattered than we've seen before. And in fact, 98% of the local gravity that we see on the moon is associated with topography. Only 2% is due to other gravitational structures in the crust. But that 2% actually tells us something extremely interesting, and we'll hear about that from one of our other panelists. So I'm going to now turn it over to Mark to talk to us about the lunar crust.
Okay, thanks. Next slide. Okay, so one of the first scientific results from the high-resolution gravity data from GRAIL was to determine the density of the moon's crust. And this graphic here is showing the crustal density centered over the near-side hemisphere on the left and the far-side hemisphere on the right. And the first point I'd like to make is that the crustal density of the moon is not constant. There are large lateral variations, which are really important. For example, these can be due to changes in crustal porosity, or they could also be due to changes in the density and composition of the crust. So if we take one example, which is the South Polacan Basin on the far side, which is shown by this circle here, this is the largest impact basin in the solar system. It's about 2,000 kilometers in diameter. And this region has a higher than average crustal density, and this is simply because this region has been known for a long time to have an atypical iron-rich composition. So next slide. Okay, so next what we can do is we can use independent estimates of the density of minerals in the crust of the moon. And this comes from using data from the Apollo samples, but also from compositional data obtained from orbit. And then we combine this with the GRAIL bulk density results, we can estimate the porosity of the surface. Now this graphic here shows the same thing where high porosity is in red, low porosity is in blue. And the first point I'd like to make is that the average porosity of the moon's crust is 12%, which is extremely high. And as Maria just said, this is simply a consequence of the fact that over billions of years of solar system evolution, a large number of asteroids and comets smashed into the surface of the moon, fracturing the crust and generating porosity in the process. Now what this graphic also shows is that there are strong lateral variations, changes in porosity from place to place. So if you look at some of the youngest large impact basins on the moon, such as Moscovians and Oriental, we see that these two basins are surrounded by regions of crust with an extremely high porosity of about 20%, which is simply a reflection of the impact process fracturing the crust. Now what we also see is that in the interior of some basins, the porosity is lower than average, as shown in blue within these circles here. Now this is simply a reflection of the fact that when you form an impact crater, the interior of the crater is extremely hot and partially molten, and this tends to reduce porosity. So next slide. So here what I'm going to show is a crustal thickness map of the moon that was generated using the GRAIL gravity data and also topography data from the Lunar Reconnaissance Orbiter mission. And the first point to make is that using the GRAIL gravity data, the average thickness of the moon's crust is found to be between about 34 and 43 kilometers. Now these numbers are about 10 to 20 kilometers less than previous estimates that were based on previous missions from Kaguya and also Lunar Prospector. And because the moon's crust is extremely important for understanding the bulk composition of the moon, what these results show is that the bulk abundance of aluminum in the moon is exactly the same as that of the Earth, whereas previous studies suggested that the composition of the moon may be different than that of the Earth. So what this is consistent with the hypothesis that was recently shown in a couple of science papers 2 weeks ago, that the moon is most likely derived from materials that come from the Earth following a giant impact event. What I'd next like to point out here is that you can see there are regions of the moon's crust which are extremely thin, these blue regions here which correspond to giant impact basins. And these are simply a reflection of the fact that when you have an asteroid that's 100 kilometers in diameter, it smashes into the moon, you dig a big hole. And in some cases, these impact events could excavate all the way through the crust and into the underlying mantle. So next slide. Okay, this last graphic here, this is just showing the crustal thickness of the moon in map form. And what the difference here with this slide is that what I'm superposing on this by these stars here, regions of the moon which have an atypical olivine-rich composition, which has been determined from compositional data from the Japanese Kaguya mission. And it's been interpreted that these regions of high olivine concentration are representative of mantle materials. Now, what this graphic shows is that the highest concentrations of olivine-rich materials on the moon, in fact, surround the two impact basins where the crust is predicted to be absent. So this is the Crisium Basin on the near side and the Moscovian Basin on the far side. So this is consistent with the fact that these two giant impacts excavated all the way through the crust into the mantle and exposed mantle materials on the surface. So for the next talk, we'll hand it over to Jeff Andrews-Hanna.
Thanks. So Maria told you that roughly 98% of the gravity is a result of the topography, but in that remaining 2%, there's a lot of important information, and that's what we're going to be looking at here. And I'm going to show you evidence for volcanic structures beneath the surface of the moon that are hidden from view from any other instrument and can only be seen by GRAIL. So if we can go to the next image. We started with the Bouguer gravity that you saw earlier that arises from the subsurface, but we wanted to highlight these hidden structures. So to do that, we calculated the gradients of the Bouguer anomaly that you see on the next image. And when we look at these gradients, we see a wealth of very fine subsurface structure that GRAIL is revealing. And we see a number of things that we expect in these gravity gradient maps. We see the giant impact basins and the ring structures that surround them, but we also saw some features that we didn't expect. And in science, it's the unexpected that's oftentimes the most interesting. So if you go to the next image, we also identified a large population of linear gravity anomalies that were previously unknown to science. So these linear anomalies have lengths of up to 300 kilometers, or up to 300 miles across the surface, and a large number of these. So in the next slide, we're going to look at a few of these linear gravity anomalies up close. So here we're looking at an anomaly near the South Pole Lake and Basin on the far side. And we're looking at the gravity gradients on the left, where reds and blues show steep gradients in the gravity, and then the topography on the right. And you can see that linear anomaly very clearly as a dark blue line in the panel on the left. But you look at the topography, and we don't see any expression of it at all. All we see is an ancient cratered surface. What that's telling us is that that gravity anomaly formed before the majority of the craters on the surface of the moon. So it's a very ancient structure. Go to the next slide. Here we're looking at a gravity anomaly near the Crisium Basin. So Crisium is one of the basins on the near side of the moon that's filled with dark basalt or lava. If you can picture the man on the moon, Crisium would be one of his eyes. But at Crisium, we see a linear gravity anomaly crossing the basin, but it disappears inside the basin. It's been destroyed by the impact. So this tells us that this gravity anomaly formed before the Crisium Basin. So these anomalies formed before even the man on the moon. So they're very ancient structures. And if we go to the next slide, we want to understand what the source of these gravity anomalies are. And gravity tells us about mass below the surface. If you look at the plot on the lower left, we see that these anomalies have higher gravity than their surroundings. And we're able to use models to show that that's what we would expect from a structure, a volcanic structure that we call a dike. So a dike is basically a solidified magma-filled crack. These dikes form beneath the surface. But on the Earth, sometimes we actually see them exposed. So on the right, we see a picture of a dike exposed at Shiprock, New Mexico, where we can see it because the surrounding rocks have been removed by erosion. So GRAIL is showing us this giant population of dikes on the moon that we didn't know about before. But what's that telling us about the evolution of the moon? If we go to the next slide, in order for these dikes to form, the crust has to be extending to make room for the magma. And that's what we would expect if the interior of the moon were expanding. Whereas the interior expands, the crust fractures, and that allows magma to well up into those cracks. So we can explain these if the moon were expanding in its earliest history, because these are very old structures. But that's actually the opposite of what's been happening for most of lunar history. See, for the past 3.5 billion years, the moon has been gradually cooling down and contracting. But we're saying that first billion years, it was warming up and expanding. It turns out that was actually predicted by theoretical studies a long time ago. See, we think that the moon formed in a giant impact with the Earth, sending debris out into space that collected to form the moon. Well, the process of building a moon out of that debris should result in a situation where the moon is cooler on the inside and warmer on the outside. And then what naturally happens is that the interior will warm up and expand during that first billion years. So this had been predicted theoretically a long time ago, but there's no direct observational evidence to support this period of early lunar expansion until this GRAIL data. If you go to the next image, I'll just leave you with an image of this gravity gradient map that we've used to discover this population of giant dikes and this early period of expansion on the moon. And now I'll pass the mic over to Sammy.
Good morning. First slide, please. So you've heard some of the science highlights from the GRAIL mission, from what we call the prime mission data acquired in the period March through May of this year. But these results are only going to get better because the mission did not end. In fact, after a 3-month break, where we adjusted the configuration of the spacecraft to optimize the incident sunlight on the solar panels while maintaining the precision formation flying, we found that we had enough fuel to carry out another 3-month mission that we call the extended mission, and that's in progress as we speak. The major difference between the prime and the extended missions is the altitude, where we halved that altitude for the extended mission. So by the nature of the 1/r² physics of gravity, if you approach the target you're measuring by a factor of 2, you increase your resolution by a factor of 4. So we are opening another window in terms of the geophysics, and we've defined a new set of scientific objectives for the extended mission, and we're acquiring the data. So you'll be hearing results from that in the near future. And just to help you visualize the next slide, please, the resolution as we go from a 55 average altitude, 55 kilometers, to 23, this is simulated imagery of the surface of the moon to see the increased resolution as we halve the altitude, just to aid in the visualization. The next slide, please. So in fact, speaking of images, one of the other payload instruments on the GRAIL spacecraft, both Ebb and Flow, was a series of cameras called MoonCam, and these were coordinated and operations carried out by Sally Ride Science Institute, obviously led by the late Sally Ride, and based in San Diego, where we had school children from over 3,600 schools from 64 different countries registered to participate, and the kids could select targets and let us know, and we would actually take pictures of those areas once we fly over them, and we've made over 100,000 images available so far from the prime mission only for educational purposes. So Sally Ride had dedicated most of her time for educational projects, and we've helped with these images from the moon to get the next generation excited about lunar science. This image, I believe, is from one school taken exactly 1 week ago, Webb Elementary School in Newark, New Jersey, where there was a lot of excitement about the recent images we got from GRAIL. And the other image, I should say, is the Operations Center of Sally Ride Science, SRS, on the campus of UC San Diego. Next slide, please. And this is a flyover of Anomaly Basin on the moon, taken from the MoonCam images, specifically Flow spacecraft. And Anomaly is the subject of a lot of geophysical interest, and we have a lot of studies going on to examine that, especially in the extended mission with the high resolution, where we actually fly over the rings by about only 2 kilometers above that, so we're very close. When I said earlier 23 kilometer, that's average altitude, so when you account for the topography, sometimes we get very close to the surface. So with that, we expect a lot more exciting results in the future, so stay tuned. And I believe that's the last slide. Thank you.
Hello, hello. Okay.
Hi, I'm Alex Witze with Science News. My question is for Jeff Andrews-Hanna. Can you talk a little bit more about why the moon would have been expanding early on and what caused the change from expansion to contraction and when?
Certainly. So most solids will expand when they're heated. So most solids will expand as they're heated. So they warm up and they expand. So if the interior of the moon were warming, it would expand. And the reason why we think the interior of the moon was warming is if you look at the temperature profile of the moon after it forms, like I said, it would be cooler inside and warmer outside. And that's a result of the process of building up a moon from the impact-generated debris. You're converting gravitational energy to heat, and the moon gets warmer as you go to the outer layers because of the impacts of that material. So we would expect there to have been a period where you had this thermal inversion of a cool inside, a warm outside, and then as the moon comes into thermal equilibrium, that inside heats up, and that's what would cause the expansion.
And when does that transition happen?
According to the earlier modeling studies that study this theoretically, it would be after about 500 million years to 1 billion years. So the first roughly billion years of the history of the moon, it would have been undergoing this period of expansion.
Jonathan Amos, BBC News. So what does this tell you about the nature of the late heavy bombardment? Was it more severe, less severe than we thought? And any clues to those highlands on the far side? Any ideas yet? I mean, there was just before you launched this Nature paper that came out that said they may have been the result of a low velocity impact, you know, subsuming this object.
I'll take that. Okay. So what this means for the late heavy bombardment. So we're in the process of analyzing that quantitatively. One of the things that we can do with this data is you need to understand the inventory of impacts very precisely. And because the moon has been so battered, there have been suggestions of partially preserved impact craters, large impact basins, which have been debated by the community. Okay? However, as you can see by looking at the Bouguer map, where the effective topography has been removed, all large basins have a positive gravity anomaly associated with them. And so it's possible not only to determine what is actually a basin, but how large it is, and that allows one to calculate the energetics. So we are right now in the process of refining that basin population, and we will be able to, at minimum, reduce the error bars in what the actual impact population is drastically. Okay, so that's a work in progress, and you'll be hearing more about that soon, I hope. The other question was, what about the far side, and the question about the far side highlands corresponding to the idea of a second moon. And we on the team see no evidence for that on the basis of the Bouguer map. You know, we think that there ought to be chemical evidence associated with it, and that hadn't been seen. But gravitationally, there is not anything about that particular region that was proposed as being different to first order from other areas of the highlands. And of course, you know, all of this needs to be analyzed in more detail, and perhaps subtleties will arise. But to first order, we don't see evidence for that. We have not found evidence in support of that hypothesis. Let me phrase it that way.
Paul Doherty from the Exploratorium, San Francisco. Do you see time-dependent effects from, like, tides from the sun?
Okay, I'll address that. So studying the deep interior of the moon and the time variability of the field is one of GRAIL's objectives. Okay, and in order to do those studies, it requires extremely precise corrections on the data. The biggest error source is the pressure of solar radiation, of solar photons pushing on the spacecraft. So at any given, you need to know the orientation of each spacecraft at any given time and where it is with respect to the moon's surface and the sun. So these are tiny, and if you want to see in my talk this afternoon, I'm going to show an image or a figure of showing you that correction. However, I had to pull the team off of doing those levels of corrections because when we went from an altitude of 55 kilometers down to 23 kilometers, what we needed to stay in orbit around the moon was the highest possible spatial resolution gravity field where those corrections didn't matter, okay? And so during the primary mission, we only needed one maneuver the entire 3 months to just adjust the drift rate of the spacecraft. But in the extended mission, we're a factor of 2 lower. We need to do 3 maneuvers a week just to avoid crashing on the moon. So yes, we're back on it, you know, or we'll be back on it with abandon very shortly. But it had not risen to the top of the list in terms of the operational requirements to do the extended mission.
I have a question from the internet. This is from Camille Carlisle with Sky and Telescope magazine. And Camille's question is, why would the high porosity have to be a result of pulverization by impacts? Could the porosity be a byproduct of how the moon formed?
Well, people think that when the moon formed, it started out very hot. In fact, the current hypothesis is that when the moon formed by a giant impact of a Mars-sized object into the Earth, when that material reaccreted to form the moon was probably in a completely molten state. So if you start out with something that's molten, it's not going to have any porosity in it. So the porosity that we see in the crust was most likely generated after the crust of the moon formed, maybe tens of millions of years after the formation of the Earth-Moon system. And in terms of other processes to generate porosity in the crust of the moon, I can't think of any. The easiest way is just to you smash something into the surface, you fracture it, and that generates void space, which gives rise to porosity.
Thank you. I have another question from the internet. This question is from Leo Enright of Irish TV. Do you anticipate a scramble to reevaluate Apollo and Luna data in light of the Dike discoveries or other results? Do any major new features appear near historic landing sites?
I think these dikes, there will be a lot of work trying to understand what they mean for lunar evolution. In terms of the Apollo missions, I think one of the things that we'll want to look at is, do any of the rocks that the Apollo astronauts returned actually reflect these dikes? And that's possible. We can't actually tie these gravity anomalies to any particular rock. We can say things about density. But of the rocks that the Apollo astronauts returned, some of them were rocks that formed as these igneous intrusions deep beneath the surface that could be candidates as the possible things that might make up these dikes. So we can't say that definitively, and I think there will be more work on that.
Well, I just should add is that there should be a rush to reanalyze all Apollo data. And just as one example of that is concerning the crustal thickness modeling. Because following just in the Apollo era in the 1970s, when the first analysis of the Apollo seismic data suggested that the crust of the moon was 60 kilometers thick. Now, it wasn't until about 20 or 30 years later when these data were reanalyzed and the seismologists, using modern techniques, determined that the crust was in fact quite thin, as much thinner than previously suspected. So much of this data was collected a long time ago. It's a treasure trove, and I think people should be motivated to go back and reanalyze all the Apollo data with modern analysis techniques.
Casey Dreyer, the Planetary Society. Has there been any planning yet about where the 2 GRAIL spacecraft will be deorbited on the moon? And if so, are you planning to use or tie it together with LRO to observe the crash onto the surface?
Well, we're in the process of working all that out right now, and we'll get back to you next week on that.
Sorry, Olive Morton, The Economist. Is this expanding early phase of the moon, would that apply to other relatively small bodies, and would you expect to see similar dikes on Mars, for example? And second question would be, you showed us that the dikes the dikes in general don't have outcrops on the surface, don't seem to have outcrops on the surface, but are there any? Have you managed to find any where there are interesting linear features that match the dikes?
Good question. So first, in terms of other planets, one of the important things to note is that if these existed on other planets, with the data we have now, we couldn't see them because the data we have from the moon is so much better than what we have from any other planet. And I think that really should motivate more missions to other planets to map their gravity fields. In terms of whether we would expect to see them, that will all depend on the thermal history. For the moon, we think that the outer parts of the moon were molten during its formation, possibly not the inner parts, and that could result in this early phase of expansion. For larger planets, it's possible they may have been molten all the way to their core, and maybe you wouldn't see that in that case. So it may differ for different planets. And then in terms of whether we see anything on the surface, possibly outcropping, I think there will be a lot more work looking for evidence for that. But so far, in every data set we've analyzed, we don't see them in any other data set. And part of that is because they're deep enough below the surface that they may not be exposed at all. The tops of these dikes may be about 10 kilometers below the surface, or about 6 miles, which would take a pretty deep crater to excavate down far enough to where you actually see that. But we've looked in topography data, we've looked in remote sensing data, and image data, and magnetic data, and so far we only see these in gravity, so this is a real GRAIL discovery.
Just the scale, how do they compare with something like the Great Dike of Zuber?
Very, very good question. So, in terms of scale, compared to typical dikes on the Earth, which these are much smaller. So typical dikes on Earth are only a few meters to tens of meters wide, whereas these are kilometers, up to tens of kilometers wide. So these are quite a bit bigger than typical dikes, but we do have some structures on the Earth. The Great Dike of Zimbabwe is one that's fairly comparable to these lunar structures. The lunar structures are bigger still than the Great Dike, but they're in the same ballpark. And we have evidence on Mars for possible giant intrusions of a comparable scale as well. So these sorts of giant igneous intrusions do exist in the solar system.
I have another question from the internet. This is from Nancy Atkinson of Universe Today. Could the team explain how GRAIL's findings can tell us more about the history not only of the moon, but of Earth and the solar system as a whole?
Okay, well, I'll start on that one, and anybody else can jump in if they want to. So if you look at the surface of the moon and how heavily cratered it is, all terrestrial planets look that way, okay, including the Earth. Okay. The Earth's record is not preserved from that earliest period of heavy bombardment because of subduction, erosion, and other processes, the oceans covering up the material. So if we want to study those early periods, we need to go somewhere else to do it, and the moon is the closest and the most accessible example. So the finding that I discussed in particular, which is the incredible fracturing of the upper crust. We now know that the upper crust of terrestrial planets is a lot more fractured from impacts than we had thought previously, and we also have reason to believe that these fractures penetrate deeper than they had than originally thought. Perhaps in the case of the moon, into the mantle. And so if a crust is fractured, it very much affects things in the evolution of a planet, such as the way a planet loses heat. In the particular case of Mars, fractures provide a pathway for fluids, fluids either rising from deeper in the planet or fluids that were on the surface that sink in. So Mars, we believe, might have had an ancient ocean, and we're all wondering where it went. Well, the neutron spectrometer data tells us that ocean could well be underground. We see evidence for very high concentrations of water. And the idea that fractures can penetrate now very deeply into the crust means that there's a pathway for surface water to go very deeply into the crust. So on Mars, say, where you have the climate changing and becoming less hospitable, if there ever were microbes on the surface that had head away to a better environment for them, they could have gone very deep within the crust of Mars. So it opens up possibilities like that, and really opens a window to this early stage of just what a violent place the surfaces of all terrestrial planets were early in their history.
Yeah, if I could just add a small comment. The main point is that all the planets have been affected by impact cratering, But in my opinion, the best place to study the impact cratering process is the moon, because the moon doesn't have an atmosphere, it doesn't have oceans, there's very little erosion on the surface of the moon, there's very limited amounts of volcanic activity. Whereas if you go to the Earth's surface is very young. It's 200 million years or so on average, and all the craters on the Earth are heavily eroded, and they're really not in a pristine state. Even if you go to Mars, there's lots of sediments on the surface, so it's not easy to study the impact cratering process on Mars as well. So the moon is the type place to go to really understand how impact cratering affects the planet. And then once we understand how it affects the moon, we can use these results to extrapolate to other planets.
Harvey Lyford, freelance. I would like to ask Professor Zuber if you could just go back to the very beginning and explain again how GRAIL actually works. It's looking down, obviously, and they're also looking at each other. So could you just, again, say what the process is by which you get your data?
Oh, okay. All right. So, it's worth talking a little bit about how we normally measure planetary gravity. Okay, so you don't actually even need an instrument. So every spacecraft has a radio on it, and the radio has a known frequency. And so if a spacecraft is in orbit around a planet, we just look for small shifts in the frequency of the radio signal. And as the spacecraft is coming towards us, it gets blue shifted. So it goes, as it moves away from us, it gets red shifted. So that's just the Doppler shift. And the Doppler shift from freshman physics, it gives you velocity. And the derivative of velocity is acceleration. And acceleration is units of gravity. So if you can subtract away all the accelerations on the spacecraft that are not due to gravity, then what's left is gravity. Okay? So that works great if the planet rotates so that you can track it from Earth at all points on the surface. But the moon, because the moon is in what we call synchronous rotation and only shows us one face to Earth, we haven't been able to directly track the far side. So then what do you do then? So you put another spacecraft there and you let the two spacecraft track each other. And so the principle of how this works is that one spacecraft chases the other spacecraft around the moon. So the course distance varies from 60 kilometers apart to over 200 kilometers apart. But the fine spacing will change based on the distribution of mass, both at the surface and below the surface. So as the first spacecraft, say, goes over a mountain, which is a positive mass, it will be attracted to that greater gravitational mass, and it will speed up relative to the other one. And then the second guy comes along, and it'll speed up. So this essentially accordion type change in velocity can just be converted. We just take the derivative of that, and that gives us an acceleration. So that's essentially the way that we measure gravity with this. And we're doing it constantly. We make the measurements 5 times a second, and so we're constantly measuring this. And so it's really, what I tell people is that conceptually, it's exceedingly simple because we're just measuring the distance between 2 points, but we're doing it exceedingly well. I mean, in order to do this, we will occasionally track the spacecraft from Earth. We have to, compare the timing with a extremely accurate clock on Earth, and we even correct for general relativistic effects and tectonic drifts of the plates of the tracking stations that are on the Earth. So these are the levels of the corrections that we need to make in order to measure gravity that precisely.
Jonathan Amos again, just to follow up Harvey's question. It's sort of kind of a two-part then. You can get very fine point measurements on Earth with instruments, but am I right in thinking that actually this is a better global map of gravity than we have of the Earth? And also, because the data is such an extraordinary affirmation of the concept, is there any talk about flying a GRAIL mission to Mars, proposing it in a Discovery class or something like that? Do you know if there's any discussion about that?
there are certainly discussions about that that are going on, and somebody would have to propose that to happen and have a very good scientific justification. This gravity field is the best gravity field for any planet, including Earth. Okay, and we have at the Moon we have so of course GRAIL was based on the extremely successful GRACE mission, which is a 2-satellite mission which has been orbiting the Earth and is still orbiting the Earth and collecting great data, focusing on the time variability of the field. But GRACE, because the Earth has an atmosphere, GRACE is at 500 kilometers. So you just can't get the, nothing beats going low, okay? So we have a similar measurement sensitivity. Actually, we're performing a little better than the GRACE instrument because we learned from GRACE, so we were able to make some very judicious improvements. We also don't need to correct for atmospheric drag, which even at 500 kilometers altitude, GRACE needs to carry an accelerometer and correct for that. So we're in a special situation at the Moon where we're able to make these measurements this well. And certainly this concept could be extended to study other things. I mean, you could study the circulation of Venus's atmosphere, which is very massive, and look at the time variability. Imagine taking a concept like this and mapping currents in the ocean beneath Europa. That could be done with a concept like this. So, so when you can measure something extremely, extremely well, discovery is assured.
Rick Lovett, freelance. I have a very technical question. Early on, you said you could measure to some number of nanometers per second, and I heard either 15 or 50.
Oh, 50, it's 50 nanometers per second.
50.
Yeah, 50. 0.05 microns per second.
Monica Sanchez, German Public Radio. Can you again tell me how the core can expand if it's cooler than the outside?
Well, the expansion is a result of warming. So planets want to be in thermal equilibrium, and what that entails is an interior that's warmer than its exterior. So on the Earth, as you go deeper and deeper beneath the surface of the Earth, the temperature gets warmer and warmer. And that's a state that planets want to be in from a thermal standpoint. So if we had this early state where the interior of the Moon was cooler than the outside, then as that tries to equilibrate, the inside warms up and the outside cools down. And that's what gives you your expansion.
Okay, we have time for one more question. Any takers? I guess not. Okay, well, that's it then. Thank you very much, speakers, for being here and telling us about your fascinating results. And thank you everyone else for coming and asking questions, paying attention. And we'll have our next press conference at 10:30, which we're calling Earth at Night.